Hi, this is ET370 Lecture 10, and today we're going to talk about binary. We're going to go over the motivation for binary, and we'll actually talk about what we're familiar with base 10, because we have our 10 fingers and toes. Then we'll look at base 60, because that's another base we've seen. We'll look again at base 16, which is hex. And when I say again, we talked about this in lab a little bit with the RGB. And then we'll go into base 2, which is our binary, it's going to be our new friend. And we'll look at some common terms as well and some common Arduino data types. All right. So let's look at this binary system. It's a base 2 system. And so I think you guys all know you use ones and zeros, right? And the question first is why? Why would you use ones and zeros? Well, it ends up being easier and more reliable to transmit and store data. We've been talking about transistors. So transistors allow us to easily store a high or low voltage, okay? And it's more reliable to transmit. Now, we've been using potentiometers in the lab, and you can get analog signals, right? Now, the problem with an analog signal is it could be noisy, and the data, if you're sending it and transmitting it, could be easily corrupted. It's also hard to how do you store an analog value, right? Now, digital is nice. It's robust because even if it's noisy, it's a lot easier to tell the difference between a high and low value than it is for an intermediate continuous one. Okay. Now, in a following lecture, we will need a way to convert between binary and our intuitive base 10 system. But for now, we just want to go over the motivation of this and just look at what is it, okay? Now, just as an example, here's two waveforms, right? Let's say this is a desired analog signal, right? But in reality, with the electromagnetic interference, you might get a little bit of noise. And so this noise could cause problems, right? Now, if you had a digital signal, let's say this is your desired digital signal, and let's say you still have noise, so you can't get rid of the noise. But if you define two thresholds like a high and low threshold, you could easily tell that in this time interval, this is a high, and this is a high, this is high, and this is low and low, right? So I hope you can see from these two visual plots that an analog is actually undesirable in some sense, right? Whereas a digital is much more reliable. Okay, but there's a cost, right? You have to do some conversion from analog to digital and back. Okay. All right. So the first question is, well, maybe what does base mean, right? Because we have base 1, 2, base 10, base 60, base 16, base 2. Well, what does base even mean? Well, one way to think about it is how many numbers until your pattern repeats, right? And so, for example, base 10, we also call this decimal, right? By the way, it repeats every 10 numbers. All right. So let's count, right? We're going to go back to like kindergarten here. So we have 0 through 9, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And notice there's 10 numbers, even though the highest number here is 9. Okay, because I have the 0. Okay, and that's going to be a common theme, by the way. It's just similar to arrays when we looked at it in the lab. Okay, so what do we have here? 0 through 9, and then what do we get next? We get a repeating pattern, 0 through 9, but then we add a 1 here. So we get 10, 11, so on and so forth. And then you notice when we get to the 20s, it's the same thing, 0 through 9, but then again, we add a 2 here, okay? So you can see the pattern repeats after every 10 numbers, all right? Okay, what's another base that we are familiar with? Well, think seconds and minutes. If you look at your microwave, it's a base 60. And so you'll see that it's counting 0 through 59, right? Think of these are seconds. But then after 59, what do we get? We have 1 minute, and then we go back to seconds, right? So 1 minute here, and then 0 through 59 seconds again, okay? And then if you go to 2 minutes, the same thing. You have 2 minutes and then 0 to 59. So base 60 is time, right? So seconds and minutes, right? We also have base 12 and base 24 if you think of hours and days and stuff like that. Okay, what's next? Base 16, we talked about this in lab, but now I want to show exactly what it means. Okay, and so 16 numbers, so you have 0 through 15. I think you guys are seeing the pattern. Base 60, There's 60 numbers here, base 16. There's 16 numbers until the pattern repeats. And what happens? We have 0 through 15 again, and then we add a 1, right? And then we do the same thing. We have 2s in 0 through 15. But I think you can see it gets weird, right? Because what happens here? You get this 110, that's kind of weird, right? 111, 115, yeah, kind of gross, right? Okay, so what's a solution for that to kind of get rid of this weirdness here, right? Well, what you can do is actually replace this this 10 with a letter, right? So for hexadecimal, what they do is this. They replace 10 through 15 with the letters A through F. So instead of writing 0 through 9 and then 10, 15, what they'll do is they'll write this. They'll write 0 through 9, then A, B, C, D, E, F. And then when they go 10, that's good, to 19, you have 1A, 1B, 1C, 1D, 1E, 1F, and then so on and so forth. And that's why in hex, you see this mixing of letters and numbers, right? And so one thing that's good is like, for example, here, can you see that this would have been a problem, right? How would you tell the difference between 10, which is 16 in base 10, and this 10 here? Well, if you replace the 10 with A, now you have a situation where they are unique. Okay, so here's some numbers I just highlighted here. So 9, 10, 11, 12, 13. So D in base 10 is actually 13, right? Okay, and then what do we have? So 10 in base 10 is, 10 in base 10 is A, but 10 in base 16 is actually 16 base 10. Okay, so that means you have 0, 0 is 0. This is 16, and this is actually 32. That makes sense, right? Okay, all right, and then here you have 2E, 2F for in this seconds place, right? And then this number here is 15, but this number here is actually 31 in our base 10 system. Okay, so I hope you can see how to correlate the kind of our base 10, what we're familiar with hex. Okay, and we will go into more detail about how to convert between a base 16 system and our base 10 system, and we'll be a lot more familiar, but I just want to show you what it is, right? Okay, now let's go into binary. So binary is just, it seems simple, right? Because you're just counting with zeros and ones, but it's actually a little tricky. It actually is a little tricky. So for example, let's do this. We have 0 and 1, okay? And then what's the next one? Well, the next one, so if I have 1 plus 1, right? Because I'm adding 1 here. What's 1 plus 1? Well, you want to say 2, right? It's tempting to say 2, but there is no 2 anymore, right? So 1 plus 1 actually is 10, okay? And then 10 plus 1 is 11, right? So it's very, very tricky at the beginning, right? Okay, so then what do we do here? 1 plus 1, or 11 plus 1, what is that? Well, it's actually 100, right? And then if I add 1 more to this, you get 101. Okay, so this is actually the sequence. And notice after 2, the pattern repeats. So the 0, 1 is here, the 0, 1 is here, good, right? And then you have a 1, 1. And then you can see the 0, 1 repeats, but now there's no 2, it's actually 10, right? So that's why it's a little tricky to kind of add in binary, all right? So this is how we're actually increasing our numbers in binary. Okay, and you can see this here. I actually have it outlined. If you take 1, 1 plus 1, right? If you're going from here, okay, what do we get? So 1 plus 1 is, well, 1 plus 1 is 10. So we can put a 10 and we actually can do this carry, right? And then look, 1 plus 1 again is 10. So you can see that 11 plus 1 is 100. Okay, and that should match here. Okay, and remember in binary, 1 plus 1 is not 2. It's tempting, but 1 plus 1 is 10. Okay, and again, 1 plus 1 is 10 here. Kind of tricky. Okay, so let's build out a table. Let's build out a table here, okay, of binary numbers. And let's relate it to our decimal. So let's say we have decimal 0, 0. Okay, now let's say we have decimal is 1 and binary is 1, right? Now, if I want to do 2, we know what 2 is. It's going to be 10. Good. And we know what 3 is. We're going to have 11. Okay, good. What about 4? Well, 4 is here. Okay, so 4 is 1, 0, 0. Good. And what about 5? 5 is 1, 0, 1. Okay, we have that here. 0, 1, 2, 3, 4, 5. Okay, so now if we want to build this out, we want to keep going. Let's say we want 6. So if I add 1 to here, 1 plus 1 is 10. So I'm going to have 1, 1, 0. Okay, good. If I want to add 1 again, I'm going to have 1, 1, 1. Good. And if I add 1 again, I'm going to actually do a similar thing. I'm going to be flipping all these, and I'm putting 1,000. Boom. Then you can see it starts to repeat now. Like I have 1, 0, 0, 1 for 9. And then 1, 1, 0, 1, 0, 1, 0. Notice how this is kind of coming back into play, right? And then look, what's the next one? 1, 0, 1, 1, good. And then I have 1, 1, 0, 0, good. And then I have 1, 1, 0, 1, like this, good. And then I have 1, 1, 1, 0. And then finally I have 1, 1, 1, 1. Okay, so what do we notice here? Look at this. If I have 1 bit, I can represent 0 and 1, which is 2 numbers. If I actually had 2 bits, right, I could represent 0 through 3, which is 4 numbers. If I had 3 bits available, I can represent 8 numbers, or 0 through 7. And if I had 4 bits, I can represent 16 total numbers with these 4 bits, right? And what does that tell us? Well, this confirms our equation. 2 to the number of bits is our total number of unique combinations that we can represent with this number of bits, right? And you can see that here, 4 bits, 2 to the 4 is 16. You can see this here, right? Same with here, 2 to the 3 is 8, 2 to the 2 is 4, and 2 to the 1 is just 2. Okay, so it's very similar to our dies. I told you that this was going to come back. Okay, another thing, I mean, let's just dwell on this for a moment. Can you guys see this pattern? Look at this. Look how we have 1, 0, 1, 0, 1, 0, 1 all the way down. And then look at this, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Look at this, all zeros, ones, all zeros, ones. And then look at this, all zeros and ones. So I hope you can see that every time you add another bit, right? Every time you add another bit, you're actually doubling the amount of numbers you can represent. So for example, 1 bit here, I can represent 2 numbers. With 2 bits, I can represent 4 numbers. And look at this. This pattern repeats, but now you can have zeros and ones. And then if I have 3 bits, look at this. These 2 patterns are the same. 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. But look at this. Another, I can double it, right? Because I have a 0 and a 1. And then over here, notice this here is the same as this, right? So these are identical, right? 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, and so on. And then I'm just putting another bit, 0 and 1. So every time you add a bit, you double the number of representations you can make. And that's very powerful as well, right? Because that's why with just a few number of bits, you can really vastly increase your memory size, right? Okay, let's go over some common terms. So a bit, what we said is 1 or 0. A byte is 8 bits. We've seen this before. Now a nibble is actually 4 bits. So this is actually a nibble worth of data, kind of cute, okay? All right, so maybe a question, how many different numbers can be represented by 1 byte? So we have 8 bits as 1 byte, 2 to the 8, 256. And we've seen this with duty cycle, right? Okay, so 0 to 255, that's our duty cycle, right? Analog write, pin, duty cycle, 0 to 255, okay? Okay, what about 10 bits? Well, 2 to the 10, 1024. Analog read, the output of analog read is from 0 to 1023, which is 1024 total numbers, right? So you can see that the analog to digital converter is a 10-bit version for our analog read, and our digital to analog converter for analog write is an 8-bit. Okay, so if you see the number 255 or 256, it should be screaming out, oh, that's 8-bit. So these numbers aren't as arbitrary anymore. Okay. Okay, so let's look at some common data types that we've used. So some common data types are, of course, the 8-bit, right? A byte, right? We've seen this in our lab with arrays. And so the range is 0 to 255. And so the biggest positive number here is 2 to the 8. Notice the -1. And this -1 is to count for that 0, right? So it's not 256. It is 255, but I think that makes sense. Okay. Now we haven't used an unsigned int, but we have used an unsigned long. But an unsigned int uses 16 bits or 2 bytes. And so you go from 0 to 2 to the 16 minus 1. So 2 to the 16 minus 1 is 65,535. Okay, that's a pretty big number, right? Okay, now an unsigned long is something we've used for change time, right, in our labs, and that's 32 bits, right, and that's 2 to the 32 minus 1, which is 4.2 billion, right? And remember, if we're counting in milliseconds, this will actually take a month and a half, right, worth of time, right? Okay, now notice everything's positive, right? So these are unsigned int, unsigned long, okay? Now in your Arduino, if you just call int, which we do all the time, this is actually signed, right? So you can represent positive and negative, and it's still 2 to the 16, right? So it's still the same number unique numbers as the unsigned. However, the trick we do is we go, okay, well, half of it, instead of all 65,000 being positive, we'll only take 32,000 positive and 32,000 negative. That way we kind of cut in half. So that means we take a bit off. Look at that, 2 to the 15 minus 1 instead of 2 to the 16 minus 1, because we know that adding and subtracting a bit here cuts our number of representations in half. And then we'll allocate 2 to the 15 bits down here to the negative side, okay? But still, from negative 32,000 to positive 32,000 is actually the same from 0 to the 65,000, okay? Okay, what about a long, just purely long, not unsigned long? Well, this has 32 bits, still the same number, right? Still 4.3 billion numbers, but again, similar to this, we just cut in half. We have negative 2 to the 31 and to positive 2 to the 31 minus 1, okay? Okay, now this is these are a lot of the common data types you've used, right? Especially int and unsigned long, but you could use long, you could use unsigned int, you could use byte, right? And so we've talked about ones complement in the last lecture. Ones complement was basically flipping the bits, ones and zeros. Well, two's complement is going to be a slight complication to that, but two's complement is a future concept we're going to use to describe the sign. Notice that here, when we talked about this, we're going 0 to 15. These are just positive numbers here. Whereas over here, we have negative. So we're going to use two's complement to represent these negative numbers. These are unsigned. This is just kind of like this, straightforward, right? But yes, two's complement is coming down. All right. Well, I hope this was a good intro to different bases, and it just intuitively built up. Why do we need binary? What are some different common bases like base 60, base 16, and why are base 10 is so convenient just because of our intuition? And I hope you learned something. All right. Have a great day.